Hello, welcome to this chapter 17 CH103 lecture. So this is the second lecture series for chapter 17 on spontaneity, entropy, and free energy. So in this lecture, I'm going to be looking at the free energy, and I'll be covering free energy, entropy change in chemical reactions, and free energy and chemical reactions. Let's look at free energy definition. So far we've been discussing the term entropy and how that is used in determining spontaneous process. So when we're saying that entropy is increasing, the sign is positive of S, and entropy is decreasing, the sign is negative. And we also stated that the entropy of the universe is from the sum of the entropy of the system and that of the surroundings. And finally, that the entropy of the surrounding essentially related to the temperature. So we see that in a constant temperature conditions, the entropy is essentially equal to the enthalpy over temperature. So I'm not going to go into the details of those since we are moving on from that. Now, one parameter or quantity that also helps in the determination of a spontaneous process is free energy. Free energy is capitalized G symbol, and free energy, you can see, is actually related to the enthalpy value and also the entropy value. So what it is here, you're looking at this coming from the first law sort of determination when we're looking at the enthalpy changes and the study of the various states or reactions. Here we're looking at the entropy changes, which comes in this discussion of the second law of thermodynamics. So what essentially free energy is doing is combining both the first law term and the second law term, putting them together into one big relationship, which is the free energy. So this is really one of the core parameter or term that we need to get more understanding and deeper level into in this chapter. So these are the definitions of the so temperature here is in Kelvin, and S is entropy, and these are values that are related to the particular system that we're looking at. So we'll consider that. So at constant temperature, we can say the changes in free energy is equal to the change in enthalpy minus temperature times the change in entropy. So basically, this is one of the very important relationship when we look at the whole system, that is a whole reaction system, and look at whether it's spontaneous or not, where you consider all the various factors that are in there: enthalpy, entropy, and likewise temperature. So what is the relationship between free energy and spontaneity? We can do some rearrangement in this formula. So let's just take that through. This is the equation. This is the equation we are looking at. Free energy is, that is free energy of the system. By the way, when you do not see any subscript in this sort of equations, that means system. But if you are looking at something that is with subscript, that's specific to that particular description. So these are considering a system. So if you divide this equation here by temperature, this is what you get. Or minus T. If you divide it by minus T, so it'll be minus delta G over T minus delta H over T plus delta S. So here, because delta S here will be the system, delta G is system, that is system. So at constant temperature and pressure, the term here, delta S of the surrounding is essentially this. This is what we saw from the first video. Delta H of the surrounding is equal to minus delta H over T. So we can then substitute it into the top relationship. So delta G minus delta G over T is equal to delta H over T plus delta S, and substituting this out here, that's what we get. So the argument is here. When we are looking at the change in entropy of the universe, we are basically relating it to delta G in this form. So what is different though is here. The sign here is positive, the sign here is negative. Okay, negative. So this is one of the criteria of spontaneity that we are going to be using. We already know this one. This one, when the sign is positive, we know it's increasing in entropy. That's spontaneous. But remember, when we bring in delta G or G, if it's spontaneous, it'll be negative. So delta S of the change in entropy of the universe is minus delta G over T at constant temperature and pressure. So here's what I was meaning in that. So a negative delta G means a positive delta S. So these are the variations of delta S and delta H to give you a spontaneous process, and it comes from the basically the relationship that I've shown in the previous slide. Delta G is equal to delta H minus T delta S. So in order for this to be negative, that is delta G to be negative, meaning spontaneous, then you will have to look at the variations in these values, how that will come out. So if you, in the case where delta S is positive and delta H is negative, here is negative, this is positive, this will be spontaneous at all temperatures. So basically looking at this equation and seeing the variability. So you can go through the rest of that and try and follow through on that. Otherwise, you simply have to use this equation. Now let's look at one example. So free energy and spontaneity. At what temperatures is the following process spontaneous? Okay, at what temperatures? So here you are given bromine liquid to evaporate or vaporize to bromine gas. So that's a change of state here. And you're given the enthalpy of this. This is the enthalpy of the system, which is this vaporization process. And this is the entropy change. We expect the entropy to increase, right? Because you're changing from liquid to gas. And it is plus 93.0 joules. I'd like you to note very quickly, very carefully, this is kilojoules per mole, enthalpy. This is joules per Kelvin per mole. So one point regarding entropy, the entropy of values. The entropy values are generally much, much lower than the enthalpy. And the second part of this question is what is the normal boiling point of bromine? So let's look at this. So first, the vaporization process will be spontaneous. We should know that because you are increasing the degree of disorder or the the increase in the probability of the entropy, or the probability of the microstates. That's what is happening in here. So that favors the vaporization process because the increase in positional entropy or positional probability. And delta H naught favors the opposite process. Why is it favoring the opposite process? Because this process here of vaporization is endothermic. Why is it endothermic? Well, you see it here. Let me go back. You see it here. This is endothermic. It's gain in energy. It's a positive value. Okay. Now let's go back. So these two are in the opposite action. So what we need to find out, this opposite tendency will exactly balance at the boiling point of bromine. So that's what we need to find. What happens at boiling point? At boiling point, the equilibrium between the two is established or reached. When that is reached, that will be delta G is equal to 0. Remember that when we were talking about entropy, at equilibrium, the entropy is 0 too. So delta G is going to be 0 as well. So let's see how that is calculated. So we need to establish the value of delta G for that process. That is 0 because as at equilibrium. Now we have the two values here, this delta H and delta S from the question. So let's rearrange that. That'll give you this and substitute in the numbers and you get this value. Notice that the temperature that you get from here is Kelvin. So this is 333 Kelvin. And notice that we have to change the unit of this to joules. It was reported in kilojoules, so you have to work in joules unit so that it is consistent with the joule unit of the entropy. All right. So that is a temperature. So what does that mean? So at temperatures above 333, T delta S term is going to be greater than delta H, and that will give you a negative delta G. So in other words, that temperature, which is the vaporization temperature, is actually the threshold, whether this is going to go in a spontaneous process or not spontaneous. So at above 333 Kelvin, the process is spontaneous, because if you go above, then the delta G value becomes negative. But right on 333, it is 0. And if you go one value higher, the value is going to start to drop to negative. And the opposite process occurs spontaneously below this temperature. So at 333 Kelvin, liquid and gaseous bromine coexist, and we say that it is in equilibrium. So in summary, at a pressure of 1 atmosphere, the temperature greater than 333 Kelvin, delta S controls, and the increase in entropy when the liquid bromine is vaporized is dominant. So this is a spontaneous process. At below 330, the process is spontaneous in the direction in which it is exothermic. I don't like this statement. It should be just simply say non-spontaneous. It is non-spontaneous. And at that temperature, this will be at equilibrium, and this will be right at the boiling point of the bromine liquid. All right, let's go on to another example here. A mixture of hydrogen and chlorine remains unreacted until it's exposed to UV light from a burning magnesium strip. So this is the reaction. Hydrogen reacting with chlorine, the gaseous state form 2 hydrogen chloride, and this is also in the gaseous state. So if you look at the number of gas molecules here, you will notice that there is 1 and 1, there is 2. So 2 is counterbalanced by 2. So in other words, you really cannot tell whether there is an increase in entropy or decrease. It looks like it is counterbalancing in these two. However, let's look at the thermochemical data. The free energy term is minus 45.54. The enthalpy change is minus 44.12 kilojoules. And the change in entropy is minus 4.76. Again, let me just emphasize this is joules, and these two are kilojoules. So joules per Kelvin. So what does it mean? According to this value here, this is spontaneous because it is negative, right? However, this value here means non-spontaneous. Remember that? Because if it's positive, then it should be spontaneous. This one, if it's exothermic, it favors the spontaneous. We were looking at it. That's in the surroundings. This will be a spontaneous process. Okay. So what is going to happen here is this. You will need to establish whether that is going to be the right conditions for the reactions to be spontaneous or not. So out of these choices, which one is the best? Let's take reactions are thermodynamically more stable than the products. Thermodynamic more stable than the products. That's not right, because you see that delta G is negative. Reaction has a small equilibrium constant. Not either. We don't. If it's favored to the product, then it should have a high equilibrium constant. Ultraviolet light raises the temperature of the system and makes the reaction more favorable. No, that's not also a reasonable answer here. The negative value for delta S slows down the reaction, so the negative value doesn't have anything to do with the kinetics. So this one doesn't have anything to do with the kinetics. So the last one here is the reaction is spontaneous, but the reactions are kinetically stable. That's the answer. So this one is the correct answer. We know it's spontaneous from the delta G value, but it is not immediately showing or reacting because it's not kinetically favored. Let's look at another one. A liquid is vaporized at its boiling point at constant pressure. What is true about delta G? So vaporization at boiling point. Now, one thing you should understand when you're looking at a boiling point condition. When a boiling point, that happens at constant temperature, and you're changing from the liquid phase into a gas phase. So in other words, the entropy change here should be positive. So delta S should be positive, right? Now, what is the relationship then? What is true about delta G at this? So what is important here, that you cannot just make your determination from this positive value, because if it's positive value, we'll say that free energy, that the system is in is spontaneous. It's spontaneous. But what it is that we need to work out how that relates to delta G. And we know that the system, when it is at equilibrium, delta G is equal to 0. Now, this delta G naught, that superscript, meaning at 1 atmosphere pressure, and 298, meaning 25 degrees Kelvin, 25 degrees Celsius, or 298 Kelvin. So under standard condition, this is going to be delta G naught. Delta G naught. So what is true about delta G naught for a boiling? The answer there is delta G naught is 0. So under any equilibrium, this delta G value should be 0. So entropy changes in aqueous solutions. Predicting the sign of enthalpy naught solution is difficult because the enthalpy naught solution contains large positive and negative contributions. Even if delta H naught solution is positive, it is not expected to be so large that it would overwhelm the expected positive values of delta S naught solution for this process. Overall, the effect is to make delta G naught negative, thus the solution forms spontaneously. So in other words, the use of delta G is really critical, because in that way it will see the counterbalancing of these two terms in the overall equation. So here's a solution process that is not easy to just predict. For example, here in the KCl solution, when you dissolve KCl in water, you find that this forms decim ions and chloride ions, and this shows a positive, which is increase in entropy. However, when you form lithium fluoride solution, LiF, to form lithium ions and fluoride ions, that is a negative entropy, meaning non-spontaneous. And likewise, here, calcium sulfide into calcium ions and sulfide ions, negative entropy, non-spontaneous. So what is happening here in terms of the degree of the increase in the microstates, or the probability distribution? Let's look at that. So polar water molecules are attracted to the ions to form hydrated species. So this is what is happening in the dissolution process. The assembling of a group of water molecules around the ion is an order-producing phenomenon and would be expected to make a negative contribution in solution. So hydration effect will be greater when the ion possesses more charge density. So the idea that you see here, which seems to be counter intuitive to the aspect about solution process, is really because of the hydration effect. You can see that hydration brings order, and that ordering is what we see that results in the negative. So the enthalpy changes and entropy effects must be considered to predict the solubility. So in other words, the delta H and the delta S must be both be in play or considered. in order to find out the full answer for that kind of system. For the dissociation reaction of an acid, HF, delta S is negative. Again, you see here, when we expect it to be positive, but this one here is negative. Which statement best explains why delta S is negative? Each HF molecules produces two ions and dissociates when it dissociates. Here, ions are hydrated. Reaction is expected to be exothermic and should be negative. Reaction is expected to be endothermic. So the hydration aspect is to be considered here. And that's why this will be, this is giving that negative entropy value of the system here. Now, if you look at this chemical reaction, the entropy change for this chemical reaction, ammonia synthesis. So nitrogen gas combining with hydrogen gas to give you ammonia gas. The mole ratio is 1 to 3 and 2. Now, if you look at the mole number of molecules, altogether the number of molecules on the left is 4, 1 from here and 3 for hydrogen, and 2 on the right. So in other words, in the order of positional probability that this forward reaction should be non-spontaneous. Non-spontaneous. Why? Because you have a much lesser positional probability in the product compared to the reactant side. So greater entropy, less entropy. So change in positional entropy is dominated by the relative numbers of molecules of gases, reactants, and products. If the number of products molecules is greater than the number of reactant, if the number of product molecules is greater than the number of the reactant molecules. So the positional entropy increases, delta H is positive. So that's what we expect in dealing with the gases, products, and reactants. Now, if you look at this one here, the thermal decomposition of calcium carbonate, here there is one gas molecule in the product, so you expect an increase in positional probability when you go forward in the product. So this will be a spontaneous process. Now this one here, oxidation of SO2 in air, you find that there is 2 plus 1 gas molecule and 2 here. So the reverse reaction will be the favorable or spontaneous. So this is non-spontaneous according to the positional probability based on the gases, products, or reactants. So in A, since this reaction, a gas is produced from the solid reactant, the positional entropy increases. So delta S is positive. Here the 3 molecules of gas reactants become 2 molecules. So the positional entropy decreases. So delta S should be negative. Okay, that leads us to consider the third law of thermodynamics. What is the third law? Third law basically gives you the reference value of entropy to the reported value. So the entropy of a perfect crystal at 0 Kelvin is 0. So in other words, if you're looking at the entropy change or the entropy value, that is measured relative to the perfect crystal, which is 0 Kelvin, and that is at 0 Kelvin, and the value is 0. So entropy of a substance increases with temperature. Now let's look at chemical reactions. If you look at chemical reactions, how we use entropy values in the chemical reactions. So the standard entropy values are tabulated in the book. So you will see this S naught values are given in the textbook or in the literature, and that is measured relative to the entropy, represent increase in entropy that occurs when a substance is heated from 0 to 298. So that's what we're referring to. It is the value that is reported versus, relative to the perfect crystal, 0 Kelvin. So these values are reported in the book at the ambient condition, which is 1 atmosphere. So let's look at how we can apply these values. In a given chemical reaction, the change in entropy is essentially the same way we treat the change in enthalpy using Hess's law in the first law discussion. So here the change in entropy is equal to the sum of all the entropy of the products minus the sum of all the entropy of the reactants. And of course you have to multiply that by the mole coefficients, which are this term here. Okay, let's look at one example here. So if you look at aluminum oxide, 3H2 gas, solid, to give you 2 aluminum and 3 water gas. So change in entropy, sorry, I should have put the superscript here. Standard change in entropy is equal to the sum of the entropy of the products multiplied by their coefficients minus the sum of the coefficients, sum of the entropy of the reactants multiplied by the coefficients here. So these are the values from the literature or the textbook on the entropy values of the individual. So you're multiplying this by 3 times 131, that's for the water. And sorry, this is the products over reactants. Let me just backtrack on that. So this is products over reactants. So the products are this: 2 aluminum, 2 times 28, 3 water, 3 times 189. These are the values. And products is here 1 times 51, that's aluminum oxide, and this one is 3 times hydrogen. So these are the values that are obtained from the tables in the literature. Okay, in the tables, and then substitute that into the thermochemical equation, which is products minus reactants, and you get this. And note the values that are quoted here are all in joules per Kelvin, and that's what you get. These are joules per Kelvin. What does it mean here? It's a positive value. That means it is spontaneous. Now, interesting point. Before I go on to the next slide, let me just go back here. Now, if you look at this, this is a very unique situation. If you look at the moles of gas on the reactant side is 3, and the moles of gas on the product side is 3. So in other words, here you cannot tell just by the positional entropy, that is based on the degree of probability here of disorder, that they are both gas in the 3 mole, 3 mole. So you might say they're almost zero in terms of the entropy, because they are basically the same sort of number of molecules of gas in there. But the answer is this, meaning there's an increase in entropy. Why? So this is the reasoning. The reasoning is this. You see, in the water molecule is not just one single water molecule static. You find that the water molecule actually is non-linear. It is non-linear. We know it's bend shape. and it has all these forms of vibrations, which we call stretching mode and bending modes of vibrations, or even rotational. So with all this degree of rotation or translational modes, that gives rise to the increase in entropy. So although we don't see that very clear from here, but if you look at the molecular level, this is explained by the number of molecular vibrations that are happening in the water molecule. So freedom of motion leads to a higher entropy for water molecule. So let's look at another example here. This one is change in entropy at 25 for the following reactions. So these are the values from the literature for the products and reactants. Notice that these are the values: joules per Kelvin per mole. Sorry, I didn't mention mole. So this is done in a mole basis. And then let's substitute into the thermochemical relationship. Change in entropy will be the sum of the products minus the sum of the reactants. So let's bring that in. And that gives us the answer. Let's get the value. Minus 149 joules per Kelvin. You would expect delta S to be negative because the number of gaseous molecule decreased with this reaction. Let's just go back to the reaction to verify this. See here, 3 oxygen molecules, 2 sulfur dioxide molecules. So here, 2 and 2, so these are solids, you don't care about that. But here, you look at the 2 gases, this is a decrease in the positional probability or positional entropy, okay, decrease. So let's see that in the numbers. Okay, you see that in the numbers, you see minus 149, which is a negative value, which basically confirms what we say about the gase's positional probability. Okay, these are some of the examples. I'll let you try and work through them. Predict the sign of delta S, and then calculate the delta S for each of the following. So here, let's just take this one. The gas 2 and 1. This one is a solid, this one is a gas. So 2 plus 1 here, there's 3, and this one is 2. So in terms of positional, in this direction, according to this, delta S should be decreasing, negative. And that's actually confirmed by the value calculated. So to calculate these values up and make sure you can confirm it with your visual determination based on the reaction. So once you confirm the 2, then you can move on. So I'll let you try the rest of the questions, and thank you for listening.